Well, in these card unit problems, it's often just I often have a hard time trying to figure out how I want to kind of run this. So I'm going to pick a couple of the different types of problems: a substitution problem and an elimination problem, and we'll kind of let you kind of fill in the rest as we go. Card number one, a lot of people started with this and may or may not have finished, but in this case here, it would probably be best to do the elimination method because it's not set up as y equals or x equals. And probably the easier variable to get rid of would be the y variable. And if we're solving a system, we're looking for a solution that involves an x and a y. So if we could eliminate a variable first, then we can go on to solve for the other variable, and then hopefully make some semblance of come up with, be able to plug in the answer and finish up. Anyway, to do this, I need to decide, if I'm deciding to get rid of y, I want to turn these into the same number, and the smallest number that both of those will evenly go into is 15. So to do that, I'm going to multiply the first equation by 3 and the second equation by 5. Now if I do that, I'm going to have a 15y and a 15y, but they're not going to cancel because they're both positive. So I'm just going to pick one or the other to be negative. So if I choose the first one here, make it a negative 3, then I'm going to distribute a negative 3 to all three parts there. So that's going to be a negative 21x minus 15y equals negative 18. And then as I distribute the 5 here, that's going to be a positive 20x plus 15y. And again, the point there was to have these things match and cancel. Finish up here, equals 15. Those cancel as we had hoped. These will not cancel. This leaves me with a negative 1x, and it leaves me over here with a negative 3. So I got x equals positive 3. That's my x value right there. Okay, that's part of my solution. The other part of the solution is whatever I get when I plug that 3 back into one of the x's. Okay, it doesn't matter which one. So let's go with that second equation that's a little smaller, smaller numbers anyway. I've got 4 times x, but now I know that x is 3. So I'm putting a 3 in there plus 3 times y, which I do not know yet, equals 3. So that's 12. Okay, 12 plus 3y equals 3. Well, now if I can solve for y, the next step would be minus 12 for both sides. That goes away. I'm left with 3y equals negative 9. And so if I divide by 3, I get y equals negative 3. Okay, therefore that is a negative 3. So that is my solution. Anytime you're told to solve a system, that's kind of what you're looking at. Now we move over here to number 7, and we have another situation. To do elimination would work, but if you've got a y equals, and you have something you could plug into another equation, yeah, and you may or may not kind of recognize something right away, but I'll point that out later. If I've got a y equals and another y equals, if they both equal y, then they should both equal each other. I'm basically taking this value of quote-unquote y, and I'm going to substitute it in place of that y. If y equals this, then it should also equal that. So if I put in the 2x minus 17 and say it's equal to the other 2x plus 4, now I've got these two equations equal to each other. And to try and consolidate, you find out pretty quickly here that when you move the 2x over, all the x's go away and we're left with a negative 17 equals 4, which is not a true statement. So if you have something that's not true, after you've eliminated all your variables, if they all go away, then your answer is going to be no solution. Okay. You could have also seen that up here, noticing that these both had the same slope, but a different y-intercept. So that meant they would have been parallel numbers. Okay. Yeah. I guess that's about that. Various other, I'm trying to kind of eyeball something and find out for sure if we've got another equation that might in turn do the same thing, but yeah, like this one here. Let's do one more substitution here. If we look at number 12, y equals x. So I know I can put x in place of y in this other equation. So if I say 14x, replacing that y with what I know it's equal to, minus 14x equals 0. Well, that happens to cancel. We end up with 0 equals 0. Here we had both solutions disappear, or both variables disappear, but the statement is true. The old one, the statement was false. So because this is a true statement, then we have many solutions. Okay, those are your three different possible answers for a system of equations. You can have a point, you can have many solutions, or you can have no solution.